Hi, geometry students. This is Unit 3, Lesson 8, page 365 of our workbooks. And it wants to know if these two rectangles are similar, and how do you know? Well, looking at these two, I hope visually you can tell they're not similar. Visually, when I look at this one, it's smaller. This one gets bigger, but when I look at these two, this one seems so long and narrow compared to this one. So it appears that they may not be. So let's look at some things that you can use to verify that to yourself. So first of all, you would need to be able to remember the definition of similarity. We would need to be able to do a sequence of rigid transformations and a dilation. So if I translate this 3x1 rectangle down, and then I dilate it so it's long enough. Oh, I just realized when I dilate it to get it long enough, its height's also going to rise, but this one's height doesn't change. So it looks like I cannot do a transformation and dilation to line them up. And I can verify that with my sides. So it doesn't really matter if I think about going little to big or big to little. So I'm simply going to think about this as my scale factor, which is image over original. I'm going to look at this. I'm going to make my image, if you will, the little one, and I'm going to make my original the big one. But that's just, I could do it the other direction. That part doesn't really matter. But I know that this side AD in the little one should go to side EF in the big one. I know that DC in the little one should go to HG in the big one. I know that BC, the bottom of the little one, should go to FG, the bottom of the big one. And lastly, I know the left side AB should go to the left side EF. So let's take a look at those side ratios to see if they're all equivalent. Because if these two figures were similar, the sides would have to be in proportion. That's one of my necessary parts. So this side, we'll call it 3 units long, and EF, we'll call it 5 units long. So this is 3/5. DC is 1 unit long. Here we go. HG is also 1 unit long, making its scale factor just 1 to 1. BC is equal to 3. FG is equal to 5. I'm getting my 3/5 again. However, AB is 1 and EF is 1. Since all four of these are not 3/5, 3/5, 3/5, or 1, 1, 1, 1, or if I, just for purposes of kind of getting my mind around this, if I flip-flop these ratios and put the bigger side on top, since they're not 5/3, 5/3, 5/3, 5/3, since they don't match, my sides are not in proportion, and I can verify that these two figures are not similar. For that reason, and because there is no rigid motion transformation plus dilation that brings one figure on top of the other. So these two figures are not dilated. They are distorted, and they are not a dilation of each other. So let's talk about figures that are always a dilation of each other. Those would be, for example, circles. So let's talk about what's in our summary on page 368 for a moment. So I'd like to point out that you need to read your summary on your own, but I like to point out in the middle of the page where it says all circles are similar. All circles are similar to each other, and also all equilateral triangles are similar. So both of these geometric figures allow you to translate and then dilate, and the figure is going to always line up. So let's talk about why that happens. So up here, we begin our example with just circle A and B. So I can translate circle A to B. So I'm going to translate A to B. So basically, I'm going to slide my circle A. If I get my patty paper, circle A. I'm going to slide my circle A so it's inside of B. I'm just going to translate it like that. I could have translated B to A. It doesn't matter which direction I go. Now that I'm here, if I dilate this circle to make it bigger, I can make it line up on top of B. So over here where you see that it's been moved, I now have circle A prime, and I just need to dilate it to make it the same size. So I'm going to dilate about B with scale factor. Now this is with scale factor. This is where I would need numbers. I don't have numbers in this specific example, so it's harder to do. So let's put some numbers on here. Let's say that this radius was 3, and let's say this radius is 5. So when I move it over, this radius is 3, and my longer radius is a total of 5. So that means I need to make it bigger. Remember how I do my scale factor? My scale factor is the image. It's the one that comes after over my original. So if I'm moving my little one, it's my original. If I'm moving it to my bigger one and dilating it to get it to match up, my bigger one is my image. So it would be the radius of 5 over my radius of 3. So this would be a scale factor of 5/3. That makes sense. I want this little circle to get 1 1/3 times bigger so it lines up with my big circle. Could you go the other direction? Sure, but you would need to translate from B to A. You need to move the bigger circle on top of the little one, and then you can dilate with a scale factor of 3/5 because you'd want to shrink the little one to get it, you'd want to shrink the big one to get it to sit on top of the little one. So the direction you go with the image and the original doesn't matter unless the problem tells you which direction you have to go. And then it matters whether you use 5/3 or 3/5. So this has to do with number 2 of the practice. So when you look at the practice, please refer back to this example. So I want to talk about something that's not always true. So 2 figures that are not always similar are isosceles triangles and right triangles. So let's talk about the difference. So equilateral triangles always have all 3 angles 60, 60, and 60, and all 3 sides are always the same. Let's say it's 8, 8, and 8. In this manner, it doesn't matter if I have bigger equilateral triangle or a smaller equilateral triangle. Again, I translate and dilate. Done. The only thing I have to think about is what's my scale factor. Am I dilating to make the little one bigger, or am I dilating to make the bigger one smaller? However, with isosceles triangles do not have to be similar in any way. First of all, their angles don't have to match. I could have 70 and 70 and 40. And over here I could have 72, 72, and what would that be, 36? So in this manner, there's no way these would ever match up. My angles don't agree. That's why isosceles triangles, and for the same reason, right triangles are not always similar. Yes, sometimes they are, but I have to look at each problem specifically. But if I'm dealing with circles and equilateral triangles, I know that I can translate and then dilate by some scale factor based on the particular problem, and it would always work. So next I'd like to talk about, in practice 8, I'd like to talk about number 7. Let me grab a blank one, please. So let's take a look at this. First of all, this is a nested triangle in the sense that I have a larger triangle ABC. This isn't drawn correctly. This is my ABC, and inside of it, I have this smaller ADE. And we've looked at nested triangles. I know that these 2 are congruent because this side and this side are parallel. This angle and this angle are corresponding and congruent. This angle is in both of my triangles. So these two triangles are similar to each other. I could simply dilate about center A. I could dilate this and make it 3 times bigger to get it to line up. Or I could dilate BC by a scale factor of 1/3 to shrink it down to 2. So in this manner, I know that these two triangles are similar to each other. Triangle ADE, careful of your order, is similar to triangle ACB. And I already know the scale factor is either 1/3 or 3/1. Depends on if I'm getting bigger or smaller. So let's take a look at the questions it's asking me. So it first asked me that angle ACB is 180 degrees minus x. Let's go find ACB. ACB. Well, no, it wouldn't be 180 minus x. It is x. Those two angles would be corresponding. Angle ACB and ADB would be corresponding. So this guy would not be a measure of angle ACB is actually x degrees, and I know that. So let's take a look at B. It says the measure of angle ACB is x degrees. Yes, I just did that, so I know that that one is true, and the other one is false. Triangle ACB, so ACB is similar to ADE. So this is true. Be careful when you look at it that the corresponding angles are in the same location. If they switch these letters to AED, I would now have a false statement. So do be careful with that. So now let's see. This is AD is 1/3 AC. So AD is for my little triangle, and AC is a side in my big triangle. So this is, I could think of this guy using two different equations. Either my image equals my scale factor times my original, or I could use that my scale factor is the image divided by the original, which is actually the exact same thing. This is the same equation. So, but in order to do this, because of the placement of AD is here and AD is here, I need to think about this as this is the big triangle going to the little triangle. So the little triangle side and the big triangle side. So I do know my scale factor here would be my big side is 6, my little side is 2. My scale factor would be 2/6 or 1/3. If I was going from the big one and I was dilating to make it smaller, it's getting 1/3 the size. So it makes sense that AD, the little side, is equal to 1/3 times whatever AC was, the big side. I could reverse this. I could have had AC here. I could have had AC here. I could have had AD here, but then I would need to have 3 or 3/1 as my scale factor because that would be the little one getting bigger. So I got to be really careful and find the sides that they're talking about. And here, this is a little side, and it makes sense that it's 1/3 of the big side. So now E. E, you have not done this yet. This is actually out of place, really. But I want to talk about this one because we are going to do this one. This is not the scale factor. So some kids automatically cross this out because they see the 1/2. When they look up here, they know that the scale factor is 1/3. But this problem right here, E, is actually talking about the parts of the sides. So in number 3, this was talking about the whole big triangle and the whole little triangle that you see on the paper. This one, AD is this little part, and DC is actually a part. DC is not even the side of a whole triangle. This is a part, and this is a part. This is a part of my side, and that's the other part of my side, and together they make up the whole side. So really what they've done here is they're trying to tell me that a part over a part. So if I could think about this as a part over a part, should equal another part over a part. Well, what do you mean? So let's do my AD. Again, remember, we haven't learned this. You're going to have a whole lesson about this. I just want to show you why this is true for right now. So let's do this ratio. Let's use the AD they have in my problem over the other part of that side, which is DC. So up here, part of my side is 5. The side that goes with AD is 5. The other part is 10, not 15. I'm not using the whole side. It's not scale factor. I'm using the other part. So the other part is 10. So 5 over 10 does reduce to 1/2. So AD over DC does equal 1/2. And I can multiply both sides by DC. When I do that, this cancels. And I get AD equals 1/2 times DC. That's exactly what this says. That's why E is also true. However, we haven't really looked at parts over parts. We've always been looking at the whole little triangle, which is 5, over the whole triangle side, which is 15. And 5 over 15 is my scale factor of 1/3. Don't be confused. This is not scale factor. It's another type of problem that we do later on in this unit. Thank you.